Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on theory of numbers, lecture number 24, in which I will solve some problems on congruent modulo and residue modulo M. Now we solve a problem. Problem is, give an example to show a square congruent to b square modulo 5 does not imply a is congruent to b modulo 5. Now we solve this. Let a equal to 3 and b equal to 2. Therefore, a square equal to 9, b square equal to 4, a square minus b square equal to 9 minus 4 equal to 5 implies that a square minus b square equal to 1 multiply 5 implies that 5 divides a square minus b square implies that a square is congruent to b square modulo 5. This is number 1. Since a minus b equal to 3 minus 2 equal to 1, 5 does not divide 1 implies that 5 does not divide, this 1 means a minus b, implies that a is not congruent to b modulo 5. This is number 2. Therefore, from 1 and 2, we get a square is congruent to b square modulo 5 does not imply a congruent to b modulo 5. Proved. A congruent to b modulo m1 and a congruent to b modulo m2 implies that m1 divides a minus b and m2 divides a minus b. Therefore, a minus b is a common multiple of m1 and m2. Since LCM of m1 and m2 is the least common multiple of m1 and m2, since least common multiple divides common multiple, therefore least common multiple of m1 and m2 divides a minus b. This is number 1. Now, a congruent b modulo m M1 and A congruent B modulo M2. Double implication. M1 divides A minus B and M2 divides A minus B. Double implication. A minus B is a common multiple of M1 and M2. Double implication. The least common multiple divides common multiple. This is least common multiple of M1 and M2 divides common multiple. Double implication. A is congruent to B modulo least common multiple of M1 and M2. Proved. Now we solve the next problem. Problem is if M1 and M2 are relatively prime, then A congruent B modulo M1 and A congruent B modulo M2. Double implication. A congruent to B modulo M1 multiply M2. Since given that M1 and M2 are relatively prime, therefore GCD of M1 and M2 equal to 1. This is number 1. If GCD of M1 and M2 is 1, implies that LCM of M1 and M2 equal to M1 multiply M2. That is M1 M2. This is number 2. Since we know that A is congruent to B modulo M1 and A is congruent to B modulo M2, double implication. A is congruent to B modulo LCM of M1 and M2. Double implication. A is congruent to B modulo here LCM of M1 M2 equal to M1 multiply M2. M1 multiply M2. Proved. Now we solve the next problem. Problem is if 70 is congruent to 22 modulo 3 and 70 is congruent to 22 modulo 4, then prove that 70 is congruent to 22 modulo 12. Here GCD of 3 and 4 equal to 1. Therefore, LCM of 3 and 4 will be 3 multiply 4 equal to 12. Given that 70 is congruent to 22 modulo 3 and 70 is congruent to 22 modulo 4. implies that 70 is congruent to 22 modulo LCM of 3 and 4. This is number 1. Implies that 70 is congruent to 22 modulo, here LCM of 3 and 4 is 12. 12 using 1. Proved. Now we solve the next problem. Problem is, if A is a solution of fx congruent 0 modulo m and A is congruent to B modulo m, then B is also a solution. Now we prove this. Since given that A is a solution of fx congruent 0 modulo m, implies that in place of x we write a, fa congruent 0 modulo m. This is number 1. Also given that A is congruent to B modulo m, implies that we know fa congruent to fb modulo m, implies that fb congruent to fa modulo m. This is number 2. From 2 and 1 we get here fb congruent to fa modulo m, here fa congruent to 0 modulo m. That means fb is congruent to 0 modulo m. fb is congruent to 0 modulo m. Therefore, B is a solution of fx congruent 0 modulo m. Proved. Now we solve the next problem. So that A is congruent to B modulo m, then GCD of A and M equal to GCD of B and M. Now we solve this. Since given that A is congruent to B modulo m, implies that M divides A minus B, implies that A minus B equal to some integer k multiply M. K is an integer. Implies that A equal to B plus Km. This is number 1. Therefore, GCD of A and M equal to GCD of B plus Km and M. And we know that this equal to GCD of B and M. Here we have K multiply some integer M. Here M, here M. Then we know this equal to GCD of B and M. Proved. Now we solve the next problem. Next problem is, so that for any integer a square plus a plus 1 congruent 1 modulo 3 or a square plus a plus 1 congruent 0 modulo 3. Now we solve this. Let a be any integer. By taking modulo 3, we get residues or remainders zero or 1 or 2. When remainder equal to 0, then a congruent 0 modulo 3 implies that if a congruent f0 modulo 3, let fa equal to a square plus a plus 1. Congruent, in place of a we write 0. 0 square plus 0 plus 1 modulo 3. Taking fa equal to a square plus a plus 1 implies that a square plus a plus 1 congruent 1 modulo 3. This is number 1. When remainder equal to 1, then a congruent 1 modulo 3 implies that fa congruent to f1 modulo 3. Let fa equal to a square plus a plus 1 congruent, in place of a we write 1 square plus 1 plus 1 modulo 3 implies that a square plus a plus 1 congruent to 3 modulo 3. Since 3 is divided by 3, so here we may write 0, implies that a square plus a plus 1 congruent 0 modulo 3. Since 3 divides 3. This is number 2. When remainder equal to 2, then a is congruent to 2 modulo 3 implies that if a congruent to f2 modulo 3 implies that a square plus a plus 1 congruent, in place of a we write 2 square plus 2 plus 1 modulo 3 implies that a square plus a plus 1 congruent. This is 4 plus 2 plus 1 means 7 modulo 3. When 7 is divided by 3, remainder is 1. This means a square plus a plus 1 congruent 1 modulo 3. Since 7 is divided by 3, we get remainder 1. This is number 3. From 1, 2 and 3, we get a square plus a plus 1 congruent 1 modulo 3, and here a square plus a plus 1 congruent 0 modulo 3, and here number 3 same to this, therefore proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.